All right. So band diagrams, like I said, has two aspects to it. So what you see, these lines over here, they are the potential energy of electrons, which are called energy states of a particular configuration of a material. What I mean by particular configuration of a material is, like for example, here I've taken a crystalline silicon material, right? If I just take a single isolated silicon atom, this whole band diagram will look different. Basically, it is see, before quantum mechanics came in, people were thinking this is all one giant continuous band, that these are all possible bands, and depending on the temperature or doping concentration, a certain amount of electrons can occupy these states. But you know, during the early 20th century, when people started doing spectrometry and start seeing gaps in the spectrometers, they realized that they're discrete bands. There are only certain available levels of energy which a electron or hole can occupy. The rest cannot be occupied. So in a band diagram, what you see, a band of a particular material, like for example, silicon, you see this band gap is 1.1 electron volt, which means that in this particular band, there can be no electrons at all. That's just not possible from the physics of the atoms and their interactions with the lattice. That's not possible. These are the possible energy states. Anything below the valence band, anything above the conduction band. Now, if I take the same material, and take it to 0° K, like the lowest temperature possible, physically possible, then all the electrons which are there will all be in this valence band. That means they're all tied to their valence electron, so nothing can move. So anything in this band means they cannot move, and there will be 0 electrons in this band. Okay, so the states still exist, but there are no electrons available in these states because of their energy, because of the low temperature. And I start increasing the temperature, then slowly one of them starts jumping, leaves a hole behind. And if the hole is in this band, it's kind of reversed, then they can conduct, right? So that's the idea of basically band diagrams. Okay, and then we said we can, so this is an intrinsic semiconductor, then we said we can dope it with a dopant which has one extra electron. And if you do that, then the average electron density potential energy increases to the extent that just give me a second here. Okay, extent that it is closer to the conduction band, which means that at a given temperature, like a room temperature, you'll have a lot more electrons in the conduction band to conduct. So essentially what I've taken is, I've taken a very resistive silicon material. I kind of did some impurity injection into it, and now it's a conduction material with mostly electrons in it, right? And then you can do the same thing on the opposite side, where you take materials which has one less electron in their valence band, so 3 instead of 4. Which means that in a overall material sense, it looks like there are more positive charges here. And what that does is brings your Fermi level energy close to the valence band, and which means that you'll have more number of holes under the valence band. So basically, more number of holes will be occupying these states here. And if they're occupying states here, they will conduct if I apply electric field. So electric field applying is, you can imagine this whole line tilting. So as I apply something positive with respect to this side, then this whole thing will tilt. So the holes will move in this direction and the electrons will move in the opposite direction. Okay. And we talked in detail about the PN junction. So we take P-type, N-type, join them, and you have, because of the potential difference, you get this depletion area. And we went through this detailed sort of explanation on how to calculate the charge inside it, because that's one dependency of your threshold voltage in a MOS. And we came up with this number, which is 2 times the charge of an electron times the permittivity of silicon material times the dopant concentration of whichever side you're looking at. In this case, it's the donor, and then phi naught is your Fermi potential. And then we just quickly showed that if you apply a positive forward bias, which is basically you apply a positive voltage on the P side with respect to the N side, You take a few amount of volts, that's roughly about 0.7 volts, because that's the built-in voltage, to act against the built-in voltage. And after that, the current to voltage relation is almost exponential. But if you do the other way around, if you do the reverse bias, then you're just building that potential. You're increasing the depletion and building the electric field inside it. And essentially what it looks like, it looks like a capacitor, because I have a certain reverse bias. I add some delta V. What it does is there's no current, but there's some extra charge taken away from my battery, delta Q. And we calculated this nonlinear capacitor because basically we said it looks like a capacitor, which adds delta Q to the plates, but it increases the distance. Unlike a linear capacitor where the distance always remains constant, you're just adding charge if you increase the voltage. Here you're adding charge and increasing the distance as well. So effectively, because the capacitance is epsilon by Tox, effectively this looks like as if the capacitance is decreasing as we are increasing the voltage. Okay, and this is a crucial thing to remember, because in chip design, you basically have billions of these reverse bias diodes everywhere. Plus, your channel is actually reverse biased as well. It's a depletion, giant depletion, like we saw last time, and we'll look at it again. So it's critical to understand that. So if you look at the voltage dependent capacitor, it looks like the capacitor at when VR is equal to 0 divided by this term here, which is the Fermi potential by plus the reverse bias voltage. Now in some books or some literature, you'll find that it is 1 plus VR over phi naught. That's because the phi naught is actually included in this term here. So just be careful. So in the semiconductor physics, it's like you'll find a lot of books treatments. They just follow a little bit different here and there. Obviously, physically they have to be all same, but they follow. So just try to understand yourself first very clearly about all these terms, at least an overview of it. That way you can always figure out when you look at different material, like, okay, what they're talking about. Okay. Then we talked about the contact potential. It's kind of like built-in potential. So basically, if you stack a number of materials, what it says is that if you look at the potential across this, it's kind of a built-in potential which you have to overcome to what's called to make the band flat. So basically, you have this potential difference. That's because of the electron potential energy difference between the two materials, just like a p-type, n-type. It's kind of
So,
similar, but you have to be careful because the signs are different. So you have to be careful. Yeah, Chandan, go ahead.
so here only I had a doubt in the morning.
Yeah,
Uh,
what's
so,
the doubt?
uh, the metal to substrate the metal to substrate work function difference was negative, and the flat band voltage was also said to be negative. Means
Yeah,
we
no, sorry. Yeah, that, I
get
don't know,
that.
maybe I said it. So you can see from this diagram, this one has a higher Fermi level than this side. So let's say this was metal and this was a semiconductor. Like, so let's say this is your gate, this is your P substrate. So that's how it'll look like, right? So if you take the definition of phi ms, so this will be phi, um, uh, the electron energy is higher, but your work function is lower, because if your electron energy is higher, it takes less energy for you to get to the vacuum level. But the definition of work function, the contact potential, is actually this difference. Okay, the work function difference, which is negative in this case, and that's the voltage you have to apply to overcome. If you took EF minus EF2, that would be a positive quantity, and you have to overcome that with the negative of that amount. Did that make sense, Chandan?
So once again, I
Okay.
didn't get.
So the potential difference. So what it is if you take this material, for example, the electron energy is higher, which means that the work function is lower than this guy. Correct?
Yes.
So if I take EF1 minus EF2, it's a positive quantity. But if I take phi WM1 minus phi W2, it's a negative quantity. Okay.
Yes, sir.
the definition of contact potential is work function difference. That's why it comes negative. So in other words, if I put a metal and a semiconductor here, the built-in potential is actually positive from here to here. Okay. Which means I have to put a negative voltage to overcome it. But if you take the work function difference, it's actually negative, which is equal to V flat band. I think I might have told you that it's the opposite of work function. It's actually
Yes,
opposite
yes,
of the
sir.
Fermi potential, not work function.
Okay, sir. Thank you, sir.
Okay. So these are just terms. I would say, so that's why what I would suggest is when you take a derivation, you just concentrate on one of them, like NMOS, for example. Try to understand all the science and all the nitty-gritty details of it. Then anytime you're looking at a different material, you just use that relatively. That's much easier to kind of go through it rather than trying to go through all the science and everything, because a lot of times the definitions are opposite in some materials. So I mean, the work function is always the same, but like example, Fermi potential, uh, in some books it's intrinsic minus the Fermi energy. In some cases it's Fermi energy minus intrinsic. They're a completely opposite sign, and there is no standard for it, unfortunately. So you just make sure you understand it from a material and a voltage perspective. Like for example, when you have the gate as a metal and the substrate as a P minus, you always have to remember that you have to apply a negative voltage to make the band flat. Once you know that, then if I make one side N type, then you know that you have to reverse that. Or if I make one side poly plus, one side negative, that's because the Fermis have reversed that direction, then you have to reverse the potential and so on.
So, so
Yeah.
can we have can we have a metal gate in PMOS also? Because the Fermi level of
Yeah, of
the
course. Yeah, you can have a metal for PMOS. There is no restriction on that. It's just a different work function. So your VT will have just a different number. That's about it. Did that answer your question?
yes, yes, sir.
Yeah. You can have a metal. There's no, like I said, the metal is because of the process limitation. Like I explained last time, it melts away. That's why. And I'll explain about that process part again today. Okay, so everyone clear about this? So this contact potential thing is, I have to admit it. It's not intuitive. It's very, but just remember this much. That's it for it. Because you have to understand we're circuit designers. We're not device physics guys. So we have to understand device physics for us to help us do the circuit design. But at the same time, not like completely lie to us. But you have to understand it to the extent where you can understand devices well, so that you can make creative adjustment to circuits, but doesn't mean. Okay. So, all right. So then this is the capacitor. I don't think there's much to say here. Then I showed, excuse me. We derived the equation for conduction in a conduction material. And this I derived it because we're going to use it for our current equation for our MOS. So as uh, as I mentioned last time, uh, this once we apply a voltage across this material, you basically get a linear electric field, and I kind of showed that with a voltage divider, like a series of equal voltage divider. Why that's the case, which means it has a constant electric field. That one gives you a force on the electron, but that force, because it's a Brownian motion, just keeps banging against the lattice walls, and you eventually get a velocity which is proportional to what's called the mobility of this material. It's kind of like terminal velocity. When people do skydiving, when they jump off, obviously the g acceleration should have made it such a way that by the time they get to Earth, they're actually light speed. But obviously that doesn't happen because of the friction of the air. So at some point, that velocity just becomes constant. It's still a very high speed. Um, you can't just land on your feet, but it just levels out at some time. So it's almost a similar phenomena. So you have a force which is like G, the gravity, but then the lattices acts like air, and they slow it down. And depending on the material, this mu is different, which is a proportional constant for this thing. And as we went into when it's poisoning your mind, there are a lot of temperature and high field effects to it, which are kind of like advanced topics, which we'll maybe not go through it right now. Okay, and so we derived that. From that we found out that this looks just like a resistive material, and the sheet row. And in IC design we always take mostly sheet, because we don't have control on the H. The H is always fixed by the process, so we only control the W and the L. So when we are designing circuits and we want a certain physical resistor or a MOS or something, we can decide the W and the L. There is a max and a mean. Those are called design rules. But within that max and mean, we have the freedom to change the W and L. So that's why we always talk about sheet densities rather than volume density, because anyway we don't have access to H, so we just take that out of the picture. So if you calculate the row sheet, for example, here it's 1 over the sheet charge divided by the mobility times L over W. And like I always keep saying, that make sure you intuitively understand this and do sanity checks, like if these things make sense, because this quantity is resistance. And if it is resistance, then it should be inversely proportional to the charge density, because if I increase the charge density in this material, I'll have more number of electrons, the I will increase, which means the resistance will decrease. It's inversely proportional to mu, because mu is the proportional to velocity. So if mu is higher, that means the electrons will move faster. If they move faster, that means they will pass through a cross section faster. They'll give you more current for the same velocity, same voltage difference, and that's why this is inversely proportional. It's inversely proportional to W, because if I increase this W, then my total charge per unit length also will double. Let's say I double this double width. That means the charge flowing through this cross section per unit time also will double. That means my resistance will look like half. So that's why it's inversely proportional. Directly proportional to L, because if I increase this L by 2x, then my electric field will drop by 2x, because that's proportional to the slope of this. So I increase my dx by 2x, that means this will drop by 2x. That means the velocity will drop by 2x, and your current will drop by 2x. So that's why it is proportional to L. Okay. So this was kind of the background material for getting into the MOS operation. Any questions on the MOS operation before I start explaining we'll start from where we did last time, the threshold voltage. Any questions so far? Okay, so and like I said, before we get into the MOS, just remember the overall objective for what we are trying to do. The overall objective is we're trying to do a controlled resistor or a controlled switch, so that through a voltage we can control a resistor, or through a current we can control a resistor. So that way we can have a voltage control or a current control or a field control switch, because we're interested in digital. So we want to, whenever we want a 1, we want a switch from VDD to the output. Whenever we want a 0, we want that switch to be off, and then we want to put another switch from the output to the ground. So that's our goal. And we kind of, in semiconductor, we usually deal with 3 types of material. When we said we can't do anything with metal, right? The metal Fermi level is like embedded in the conduction band. Even though I put a high electric field, I will not be able to drive away the electrons. I can't make it non-resistive, so it is always conducting, right? So I can't use a metal. I can't use an insulator, because there is no charge inside it. It only allows the constant electric field to go through it. And so I can apply a voltage stored charge across it, but I can't flow current through it. So I can't use a capacitor. I still can use a capacitor to do digital design, but then it will be charge based. It won't be current based, but we are looking for a current based or a voltage based. So then we came to the semiconductor. So I showed you a couple of things we have done historically, like the BJTs, the FETs, how we controlled, and then we said, let's look at the MOS. So that's what we're going to look at right now. So if you take a sandwich of a a metal, which is in VLSI, it's usually a polycrystalline silicon, and I'll explain, which I've explained already a couple of times. I'll explain again. And then separated by oxide from a P-type substrate. Okay. So let's say we take this sandwich and we apply a voltage across it. So we apply some voltage VG across it. Then what's going to happen is, because we have a potential difference, some charges will build up. And because we have an oxide, those charges will result in some electric field. And obviously there are no charges in the oxide, so the electric fields will just keep going. When they reach the P-type material, the mobile carriers here are holes, right? So, but it wants electrons. So what it'll do is it'll repel the holes. And once it repels the holes, it will leave behind an immobile charge, and the electric lines of field will end there. And it'll just keep doing that and create this what's called depletion area. Depletion because it's depleted of its majority carrier, which is holes, just like in a PN junction. The only different here is in PN junction, you had an N junction here and electrons were flowing in this direction. In this case, it's a field which enters here. The positive carriers are on the metal side. And if I start looking at the voltage across this material, the key voltage to look at is at this interface, which unfortunately a lot of the books kind of miss that. They just talk always as the gate potential with respect to substrate, which is true. But the thing which creates the channel is actually this voltage with respect to your ground. So if I look at this voltage across this material, and specifically if I look at phi s is this voltage at the interface with respect to this node here. If I look at that as I'm applying the gate voltage, you're going to see something like this. So obviously across the capacitor, the electric field is constant, which means the voltage will drop linearly. Once it reaches here, then the voltage will go down in a parabolic fashion, just like it did it in your PN junction, right? So it will look like that. Now, and you can see I have drawn this line, which is a value 2 phi f, which is twice the Fermi potential of this material here. That's because what I'm trying to see is that once this potential goes higher than 2 phi f, then this will become an N-type. And I explained that through band diagram why that happens, because in a P-type material, your Fermi level is 1 phi f below the Fermi intrinsic Fermi level. If you want N-type, you want to go 1 phi up and then another phi f up. That is a potential difference of 2 phi f. Maybe I'll show that diagram again just after this. So, and that's why I put this line. I just want to see at what value of this gate voltage, slowly this will keep rising and go here, right? So you start increasing more lines of electric fields, and obviously the phi s increase more. So that's this line here, which is I'm plotting right here. So your electric field in the oxide increased. So did your depletion layer, which means your this interface voltage also increased a little bit. And then I increased a little bit more. And at that point, what happens is this potential here becomes exactly 2 phi f. And beyond that, when I increase it, all the electric field will drop across this, because what happens is a channel forms here. So it almost looks like a metal plate here. And after that, any voltage I increase, the charges here will develop and the negative charges will form here. So all the voltages will drop right here. And the electric field will just keep going up and up. But the electric field here will be just like before in the depletion area. So you will have what's called a discontinuity here. And that discontinuity here is because of this channel charge here. Okay. So, so the question now is, so the threshold voltage, so this is called the threshold voltage. So this is called the threshold voltage. It's the voltage of this metal with respect to substrate at which this material here at the interface turns into a N-type. And that's called your inversion channel, and that's your threshold voltage, right? So now I want to find out what that value is. Like, what is that voltage value? Like, is it minus 0.1, 0.2, 0.3, 0.4, 0.5. What is it? So that's what we're going to do next. So what is that value? Now, if you just write the KVL at this loop, so the VG is equal to the potential drop across the oxide, because obviously this is almost like a metal. There is no potential drop across the material. So the potential drop across this oxide plus the potential drop across this depletion area, because there is no potential drop here, because there is no the charge, it's charge neutral, right? So whatever is this potential here, it is all here, which is zero basically. So if you look at this diagram, it's zero, right? So that's your potential drop across this. So that's the gate voltage at which it will turn the channel. There is another element to it, which I showed you last time, but this is called the ideal threshold voltage. And that is the value. So VG is equal to VT when this Phi-S is equal to 2 Phi-F. So the channel is inverted. So you took a P-type material and you actually convert it into N-type. And this oxide voltage is basically all the charge which is required for you to build this depletion across this oxide, right? So Q is equal to CV, right? Let me just, so uh, Q is equal to CV, right? So you're trying to find out what Vox is. You know C, that's Cox. So basically you need to find out what this depletion charge is, and you divide it by Cox, and that will give you Vox. So that's the principle behind calculation of that thing. So basically what we are doing is we're trying to find out what the charge is, and that charge across this oxide is the voltage I need to provide this oxide charge before I get to Phi-S. So that's one part of it. Second part is this Phi-S. What is the surface potential over here? Um, and that surface potential is, like I said, that's the 2 Phi-F. That's the definition of threshold voltage. So I don't need to find out. I know that is 2 times the Fermi and Fermi potential of this p-type material. So whatever this Fermi potential is, so let's say the Fermi potential was 0.35 volt, then 2.5 or 0.25 volt, then 2 Phi-F is um, 0.5 volts. Now I took magnitude here. In a lot of the derivations, you'll see there's no magnitude. So that's where you have to be careful about the sign. I took the magnitude because for a p-type, it is plus 2 phi 5. If it have an n-type, then the magnitude will be different. So because here I'm trying to figure out what is the amount of voltage, positive voltage with respect to this, I need to build this. In case of a negative one, it's going to be the opposite, because I have to figure out how much negative I have to go below this potential here for n-type to turn p-type. So there I would keep the same magnitude, but I convert this to a negative sign. Okay, so this is called the ideal threshold voltage. But one term which is missing here is the contact potential, which I talked about last time. So as I showed in that earlier slides, if I take a sandwich like this, a metal oxide p-type, and if I look across the p-type and m-type, which is called the contact potential, doesn't matter what there is in between. All I care about is the potential, what's called the work function difference between these two types, the metal and the p-type. Okay. So for example, if I want to find out the work function for this sandwich here, then it is phi gs, which is whatever this material. So let's say this was a poly, then the work function of poly minus the work function of the p-type substrate is called the contact potential, which is termed as the flat band voltage. Now it's called flat band voltage. I won't go into the band diagram explanation of it, but typically when you join two materials, so for example, maybe I'll just quickly draw this. So if I draw the band diagram, so you have the oxide layer here and you have the metal here, and on the P side, if I draw the band diagram, you have the valence band, which will be flat like this, and it will bend slowly towards the oxide, just to make the Fermi potential same. You remember, like anytime we take a composite material, the Fermi potential has to be same throughout, right? So that has to bend to take care of this contact potential, right? So this 5GS and this bending is the amount which is 5GS. So it's called the flat band voltage because if I add a potential VFB across this, then this band will just become flat, and it'll basically give you a Q times V jump on this side of the Fermi potential. So that's why it's called a flat band voltage, because it's the voltage required across the sandwich to make the bands flat in the semiconductor area, the band diagrams flat. But if that's too much for you, it's basically just know that anytime you contact these three types material, there's a potential difference across it, which you have to come over for you to apply any charge after that. Like we were talking last time with Puneet, if I have a oxide layer and I put a metal and a semiconductor, uh, if you had a metal and metal, then you just apply V, you'll get Q. But if you have metal and semiconductor, first you have to apply the contact potential. After that only you can start applying the charge. Otherwise, before that, you actually have a reverse charge here. Okay, so just imagine that it is what you have to come over first before you can make everything the same, because the material types are different, the energies are different. So that's why it creates all these distortions. Okay, and so if you take an example, for example, this is typically like, for example, if you take a NMOS, in NMOS, this will be, um, so this will be obviously a P type or a P minus type material, and this will be actually N plus. Okay, and I'll explain why it is N plus in case of a P NMOS and a PMOS. First, I'll probably ask you that question, and then I'll explain that. Okay, so that's a term which is missing from the VT term. Just erase this here. So yeah, so if you want to find out the contact potential difference between this metal, which is, let's say, the N plus polysilicon, which is doped with, let's say, some dopant concentration ND, and your P type is um, uh, doped with Na, then the contact potential or the flat band voltage is given by this expression, which you can probably recognize. It's the same as the built-in potential of a PN junction, right? Okay, so that's the one which we have to overcome, and the value which we have to overcome is actually this quantity 5GS. So that is equal to V5FB. If you take the Fermi energy difference between those two, it has to be negative sign. But that's why I said, take one material, get accustomed to the sign. Like, for example, you take NMOS, you get accustomed to all the sign. That will give you, okay, now if I change this to P type, it should invert and so on. Okay, so um, so now if you take the VTN equation now, so previously you had this part, right, which was QB over Cox here, and this was obviously phi s, the surface potential, but you have to add this phi ms part of it. Okay, phi ms over here. So I'm taking example here. So let's say you had a oxide density capacitance density as 3.45 femto per micrometer square, and this was doped 10 to the power 15 ions per centimeter cube, or dopants per centimeter cube. And then this was doped, the N plus poly was doped 10 to the power 19, which is basically a degenerate, but it's heavily conductive. Then if you do all the calculations, you'll find out the flat band voltage is minus 0.865. The Fermi potential, twice that Fermi potential, 0.57. And you can see that the depletion voltage, the charge, is very small, almost negligible, right? But for short channels, actually, it is not. It's quite significant. This is for long channels, that's true. So if you add all this together, it turns out that it is negative, minus 0.25 volts. It's negative. Now, typically in an NMOS, you want this to be positive. Okay, we'll understand this better when we start doing CMOS gates. but just take that for granted right now. When you're designing an NMOS, you want VT to be positive, VTN to be positive, okay? So that it is normally off when your VG is equal to 0, because this is VTN negative means that even with 0 voltage across the gate and the substrate, a channel is formed. And that's primarily because of this contact potential, because the contact potential is so much higher than this that it actually bends this bands here, converts it into N-type before even apply a voltage. So which means that I have to apply a negative voltage to turn it off. And that's not desirable in circuits. You don't have dual power supplies and you usually have a one battery. So you want it to be all positive with reference to your ground voltage. Otherwise you have to create mid voltages, convert that to ground, and all that stuff, which actually we used to do that in old circuits. So because of that, we want to make this positive. So the way it is made positive is you actually, what you do is, so if you want to make it positive, that means you want higher gate voltages, you want positive charges here to have something to cancel it. And to have that, you basically implant negative ions here. Okay, if you implant negative ions here, that means first I have to overcome this, right? Because first I have to put this, so let's say this was Q implant, QI. So first I have to put a voltage VI equals to QI over COX to overcome this before I can do the depletion and phi S and all that, right? So that's the whole idea. So what they do is they actually implant this negative ions. In case of a NMOS, in a PMOS, it will be the opposite. They will implant a positive ion. Yes, Subham, go ahead. What's the question?
Uh, so the implanted ions are mobile or immobile?
Okay, you tell me, what should it be?
Should be immobile.
Okay, so tell me why.
So we have to cancel out the positive. It is, if we implant mobile, then it will conduct.
Conduct where?
If we connect gate and source, sorry, drain and source, then there will be a channel.
Correct. And so we haven't talked about it yet. So did everyone follow, or anyone has question about why it should be mobile, or it should have it should have a layer? I mean, it should. Why can't I dope it with the p-type doping or n-type doping? What happens if I do n-type doping? Because I'm going to create a source and drain here, right? Source and drain here, and apply a voltage and conduct this channel, because the whole idea is it's 3-terminal device, right? I want 2 terminals, which I'm going to call drain and source. Then I'm going to have another terminal, which I'll gate. And through this gate, with respect to this source voltage, I want to control the conductivity. So eventually I want to control the conductivity. But if I put n-type here, then it will be conducting all the time. So I have to put immobile charges so that it's not conducting in this direction, but it allows me to have a higher VT voltage. Okay, everyone follows this, or
So
any
in the
question? Yeah.
Kang book, it has been written that the VT can be increased in case of NMOS by doping with p-type impurities.
With a p-type impurities,
Yes, sir. Na,
right?
because VTH is proportional to under root of Na in the above equation.
Yes. So okay, that's a good point. So if you see here, this is Na, which is this dopant here, right? So obviously Kang is a professor, right? He doesn't design circuits. Um, so you can increase this to lower this 5GS. If you lower this 5GS, this quantity here will lower, then VTN will become more positive, and that will go in the right direction, right? Sorry, increase this. No, sorry. What do I want to do this? If I increase the dopamine concentration, sorry, decrease it. Yeah. So I want to decrease it. So the more I decrease this Na or increase the Nd, that will create a difference in the other direction. But there is a problem with doing that. When you do that, the resistivity of this material becomes so high that it becomes so high that it becomes a degenerate material. You remember I explained, I think I have it in
Yes,
this
sir. Yes,
slide
sir.
here.
Part 20.
Yeah, so you remember here that for a p-type, if I go lower than 10 to the power 15, then it becomes more resistive or becomes what's called degenerate material. Then it's not a semiconductor anymore. So that's why it is taken to the lowest amount. 10 to the power 15 is the lowest amount. And then on the gate side, it is taken to the highest amount. And in fact, it's 10 to the power 19. This one actually can become degenerate. That's fine as long as it's very, very conductive. Okay. But the P substrate, I can't afford to become degenerate because then it'll just not act like a substrate and I'll have all other problems. Okay. I'll have breakdown problems. I'll have fracturing problems and stuff like that. Make sense?
Yes, sir. Oh, yes, sir.
Sir,
Yep. Go ahead. Who's this?
yes, sir. Sir, in case of inversion, when inversion is occurring and it is inverted to N type.
Right.
So VG increases, then the electron concentration on the surface also increases. So
Right.
that's why the depletion layer, length of the depletion layer is the max. But
Sorry.
after
What is
that,
the
in
max?
linear
What is
region,
max?
when
What is max? Sorry, I didn't get that. What did you say is the max?
there's a length of the depletion region, XD.
Okay. All right. Yeah. Go ahead. Yeah. That's this maxed out
Sir,
and it
that
stops
is
there.
maximum because after inversion, when it is converted to N type, then when we are increasing the gate voltage, the electron concentration also increasing in the surface on the surface.
Right.
So, but in linear region, when the inversion is occurring and after VD equals to VD saturation, we are having a pinch of voltage and the depletion layer
We
is
haven't
increasing
Shatabdi. We haven't.
near D. So,
Yeah. We haven't. Let's just wait for when we come there. Okay. Because people will otherwise get confused. We haven't talked
yes, sir.
about pinch off yet. So just wait till that time. Okay.
Yes, sir.
Okay. Any questions? Oh, Subham, you had just remind me, Sadabdi, when we get to the pinch off, you ask me that question because if I answer now, then people will be all confused.
Yes, sir.
So how
Yeah.
they implant immobile charges?
That's a fabrication process. That's all I'll say now. It's an ion bombardment. So what they do is they vaporize. So they take the substrate, they take a ion like N plus, like a phosphorus gas, and they do an electron beam bombardment. So where they take very high speed immobile ions and bombard it into this. So what it does, it fractures into the silicon and gets lodged into the silicon. And but the problem with that is it just breaks your silicon lattices, and that's why you have to heat it. And when you heat it, then um, basically it anneals it. It makes the lattices perfect then and does all that. But the problem with that is, like I was saying, if you have any metal there, it will melt. So that's why they don't have metal gates. Okay. All right. So any questions so far?
Mobile
So
charges.
what's that? Did
Mobile
somebody ask?
charges.
Sorry, you're cutting off. You should unmute, wait for a little while, and then speak. Yeah, I'm just getting the last word. Are you still asking something or? Okay. So, all right. So we form, yeah, Subham, go ahead. What's the question?
So how do we get the immobile charges?
Did I get cut off or something? I was explaining, right?
Yes, sir. Yes, sir. But what is the immobile charge? Like we are doping electrons. Electrons should move.
No,
How are
you're
they
not
moving?
you're not bombarding electrons. You're bombarding ions. Like for example, potassium, right? If you take potassium chloride and separate them, it's a potassium ion, right? So you can take a potassium ion and lodge it inside, like for example, silicon, and it's a charge. It has a net charge of Q minus, but it is not movable because it just lacks one electron in its valence band. So it's still one electron charge, but you can't move it because it's not a free electron. It's lying in the valence band. The charge is lying in the valence band. Okay.
Yes, sir.
Yeah.
Yes,
If
sir.
it's an ion, you have to leave it in a liquid. Like for example, in batteries, they're ions too, but they're in liquids, right? In liquid, they can move around. But if you take the ion and lodge it inside a crystal, then it can't move. You have to take electron and lodge it and have that sufficient potential energy. It is in conduction band, then you can move it. But a ion, you cannot have enough potential energy no matter what. If you have enough potential energy that it goes into the conduction band, that means you have broken it down. That means that whole thing has broken down now. It's so high that it is broken down. Okay. All right.
Yes, sir.
All right. There's another element of VT, but I need to introduce the source and drain first for that. So, okay. So let's introduce source and drain now. So basically, like as I said, what we are trying to create is this voltage controlled resistor, right? So that's our gate terminal. And we want to first form a channel and then control it through this gate and then apply a voltage across this to conduct current, right? That's the whole idea. Because we want to use this in a gate. So basically for a gate like, let's say this is your load cap. So you have two resistor, one voltage control resistor from VDD, one voltage control resistor from ground. So whenever we want a one, we are going to make this VG with respect to VDD lower because PMOS, I think most of you understand that now, that this resistance will become lower, it will charge this cap. Otherwise, and this resistance will be really, really high where this current is almost equal to 0. And then in the other case, I'll turn this on and this off, right? So that's the whole idea. So what we have done so far is we have formed the channel. So we took a P substrate, and so that's your, P substrate, which is just a P minus a crystal. And then what we did was we put a voltage, a oxide. So this is your oxide. And then we are going to put a metal, which in IC case, it's a polysilicon material, okay? So we apply a voltage with respect to this. So this is, let's say, bulk. So, and let's say we ground this, and then we apply a voltage positive with respect to this. And that will give you a channel, right? A channel here, which is all electrons here. Okay. Now I need to conduct it, right? So I need these two terminals. What do I do? What two terminals do I put? Should I put a metal, put a P plus, another oxide? So what are these two types I should put over here? Maybe I should ask you this question. So who can answer this?
N
N
plus
plus.
diffusion
N
region.
plus.
Okay. Why N plus? Why not metal? Will metal work? First, let me ask you this. Will metal work? If somehow I manage to put metal here, aluminum and aluminum, will it work or will it not just work?
Sir, the substrate is P.
Yeah, so basically I dig a hole and put a lot of tungsten or copper and all that and etch it out, and then I have this metal here. But my question is, will it work? Now I apply, so let's say this is your source, this is your drain, so I apply a voltage across the source and drain. Will there be electron flow or current flow in this direction and electron flow in the other direction or not?
So in metal, no free electrons are present.
Excuse me?
So it will work, sir.
So Smritika, what is present in the electron? Like, have you taken a metal and actually put it in the AC plug anytime and see what happens? so metal has all electrons, right? It's full of electrons. It doesn't have holes, but it has tons of electrons, right?
So controllability.
What's that?
So it's difficult to control because
Control what?
the formation of channel and flow of electrons from metal to metal.
No. See, I have a big electron channel here, right? I have created magically. And I want to take a piece of metal here. And let me do this in a different color here. I want to take a piece of metal here, right? And a metal here. And then apply a voltage across this. So I just created this nice channel with a lot of electrons. And I put two metals and conduct it through this battery, apply some voltage. Will there be current flow or not? Like, will there be electron flowing in this direction or not?
Yes, sir.
Yes, sir.
Yes, sir. Flow.
Okay,
sir.
let's go one by one. Let's see. Who said no? So maybe raise your hand who said no. I'll ask him. It's okay. It's at least you're saying. Most people are just quiet. I just want to know why you said no. Okay, Nishant, why is it no?
Sir, I'm saying yes. By mistakenly, I've just raised hand.
Oh, why yes? Okay, let's ask you. Why yes?
Sir, sir, the electron will flow, sir, because
Because of what? Okay, who else? Let's see. Who's saying no? I just want to see who's no. Okay, who's saying yes? Other than Nishant. He doesn't know why he's saying yes, but he just said yes. Okay, Punyadev, why yes?
So because a channel is there and between the metals there is a potential difference, so electrons will.
Electrons will flow. What if I put a P plus material instead of metal here? Let's say if I put P plus material here, will it flow?
So P plus in holes are there, so
Okay, how about Chandan? What do you think?
So I didn't get your question. This one we
So okay, go back to metal. It'll conduct or not conduct?
Yes, sir. It will conduct.
Okay, and why will it conduct?
So it has more free electrons with compared to an N-type, and also the work function is less, so it's easier to take out electrons from the metal too.
How does the work function come into picture? Where is work
So means
function different?
I want to say not
Two
don't
sides are
want to break.
metals.
I just want to say that it's easier to conduct electrons in terms of metal because more charge carriers are present. More free electrons are present in metal than in an N-type. So
Right. And okay, so the next question was what happens if I replace this metal with a P plus semiconductors?
then it won't.
And why not?
So substrate is also P-type and wait.
No, forget the substrate. Now I'm giving you an isolated problem. You have a channel with this charge, which is just electrons. So just assume that this is a gas of like electrons.
So
Actually,
here source is at source and that is the reverse bias, so it's difficult for electrons to flow from source to that channel.
right. So you're saying basically it's like this. So two reverse bias diodes, right?
Yes,
Yeah.
sir.
So that's a way to look at it from a circuit wise as well. Okay. And from a electron hole perspective, see, the thing is that the only mode of transport here is electrons, right? There are no holes here, very few holes, which means that the question is, if I want to, for this to be flowing in the circuit, it has to make it through this to the battery back here, right? That's the whole idea. And if I want to make it through this circuit, then obviously there is electrons here and there is electrons in the battery. The battery electrons will flow here. The positive amount will go from that and recombine and so on. The question is, will it flow through this? Well, if it is a P plus, like as you said, it looks like a reverse bias diode because there are holes present, but they will recombine, but that will be a very small recombination. Whatever minority charges are there, only that much will recombine and you'll get a tiny amount of current, which is the reverse bias current. But you won't get a huge amount of current because you just don't have those carriers here. Because these carriers, when they flow in this direction, somebody has to replenish them here. But there's nothing to replenish them here. There is a charge here, there is a charge here, but the P plus will not take it. You know, there'll be some diffusion, but that's a very small amount. So that will not conduct. So the short answer is yes. Well, the short and the long answer for metal is yes. If you put metal here, you can conduct it, but you just can't fabricate them. Okay, so the fabrication is not possible to do that in metal, and it has other problems too. You know, stress and melting and all that stuff. So it just it's a fabrication issue. So you can put a metal and conduct it. It just creates a very day. And there is another thing, what's called a Schottky diode. Once you put a metal, there'll be a Schottky diode here. There'll be a Schottky diode here. There'll be a Schottky diode here, and that also will have a huge problem on how you create that channel. But if you ask me just an isolated channel with the metal plus, yes, it'll work. So, okay, now what type should I have? So I should have a N plus, right? Because I have, I want majority electrons in this so that when I put this potential difference, then the electrons will flow as a majority carrier because I don't have holes here. The holes are in this P substrate, but they're very tiny. So the majority of the carriers here are holes, and that's what makes it flow, right? So that's why I need N plus here. Okay. Now I'll just quickly show you a fabrication step, and hopefully that will kind of give you an appreciation on why that polysilicon is inside. I think I talked about it last class. So the way this is constructed is you follow the photolithographic process where you actually first do, so when you do this device, you draw what's called layout, right? So you basically draw what's called a diffusion area. Right? So this is from the top view. I'm looking from the top. So this is, I'm drawing the top view now. Okay. So when I look from the top, it is, okay, there's a question called, sir, both the metal need to be same. What if one is P plus and one is N plus? Well, you have the same problem, right? So yeah, both of them have to be same. You take one N plus, one P plus. If you take P plus, then obviously you'll have charge carrier till here. Then how do they get from here to here? So you need the electrons here as well. So yeah, you need in both of them. Okay. So the way you draw the layout, what's called the layout, is you draw this. Sorry. Draw this rectangle, and this defines your source drain area. Okay, and this is your gate. Okay, the way it's fabricated is you have a P substrate, right? First they take this and find out what is that area. So if I take the cross section of it, now I'm taking the cross section, so I'm basically cutting the top level. So it's like taking the pie and cutting it, and now I'm looking the cross section of the pie, and that's what I'm drawing here. So if I cut it, so first they find out how much area I need to do the ion implant. So what they will do is they will actually take this area and AND it with this area, okay, and then do the ion implant to do the threshold adjustment. And then take the gate area, put the oxide here, and then they'll put what's called polycrystalline silicon, and usually called poly. Okay. After they do that, they will take this mask here, this red mask here. You know, so the mask is usually it's a opening, and they'll bombard ions through this and implant the N pluses through this whole area. So it's a heavy, high-speed ions which are bombarded. Well, in this case, it's N plus, so they are actually dopants. So they are bombarded. And when they bombard this, obviously this polysilicon is also getting bombarded. So if this is getting bombarded N plus, this is also getting bombarded N plus. So this also gets bombarded with N plus. This is N plus, this is N plus. And then what they do is they anneal it. And that's the heating process. So when they anneal it, this whole thing kind of spreads. And this becomes N plus, and this becomes N plus, and this obviously this gate area becomes N plus. And what they do after that is they actually do a small titanium or palladium to make it even more conductive, because you want this to be as conductive as possible, but you can't put a metal first, because once you put a metal and you heat it, it actually melts. The metal, like aluminum or copper, which usually what's used for IC design, or tungsten, they will melt. So because of that, they actually put polycrystalline, and when they bombard it, automatically it avoids putting N plus in the channel area because the poly and the oxide blocks it. But at the same time, it actually dopes this. And that's the way you get your N plus on your source and drain. You also get N plus in the ND. So when you did the calculation for, so your metal here, this phi M now, and this is your substrate, right? So actually the substrate contact is also done here. Everything is done on the top side. This is planar circuit. Nothing is done at the back, but just for diagrammatic, for explaining, we just show that it is done at the back. So that's the reason when we did phi ms, the flat band voltage, we did kt over q natural log of Na, which is this dopant, and D, which is this dopant here, by Ni square, which turned out to be minus some 0.89 volt or something like that. Okay. Everyone follows this? So like I said, the first job for us to create a channel controlling the gate or through some field. Second part is once we conduct the channel, we need to, once we create the channel, we need to conduct it from end to end. Otherwise, just a capacitor, it's of no good, right? So that's, and that's the second part where we actually create the source and drain. And this is done for the same type with same majority carrier as the channel. So in this case, it will be N, this will be N plus. In case of a PMOS, this will be P plus and P plus. And obviously then in that case, the poly gets doped with P type, and you get a work function difference between phi M, phi N, but now it will be a positive quantity because it's the reverse. Okay, any questions so far? All right, so I'll show, okay, sorry, I drew it in a, yes, 1 second. Okay, actually, before I went there, I had this slide which I forgot. So I think we talked about this. I'll just show. Okay, so basically, we for the VT, we have talked about the ideal, the intrinsic threshold voltage, which is the flat band voltage plus the charge I need for the depletion. This is the 2 phi f, and this is, I needed to control it because we saw that this quantity was, I think, minus 0.59 volts, right? Or I forget what the quantity was. We calculate this to be, where did I do the calculation? Okay, we did it here. Sorry, a lot of scribbling. sorry. Yeah, so the example here was minus 0.25 volts. Okay, so we got 0.25 volts. So this is not 5.9. This is, we got minus, we get minus 0.25 volts, right? And like I said, typically we want this to be positive. So what we do is we implant it with negative ions, because the negative ions will give me a positive potential for me to overcome it, so that it adds a positive amount to the VTN quantity. So I'll implant negative ions. So for example, I took 2 to the power 10 to the power 12 centimeters square, which means that if I implant that many ions per centimeter square per area, I would require this much voltage to overcome it, 0.928, which means that if I add this 0.928 minus 0.5, then it turns positive. So that's how you convert it into a positive threshold quantity. Okay. So if you write the complete equation now, so you have the flat band voltage, which is the contact potential difference, which is essentially the Fermi potential of the two end points. So polygate P substrate or polygate N substrate. And then the depletion charge you want to overcome, which is usually a small amount. And this is your surface potential to invert the channel. And this implant is what's called VT adjustment. So this is where you do VT adjustment. And like something was mentioning last time, when you do standard cells, you'll find different types of um, different values of VT for different standard cells. And what they have is the layout I was showing, that diffusion area. On top of that, you have another thing called implant. And you choose a different implant. So if I want 0.68 volts, I choose an implant where this much charge will be implanted. This many ions will be implanted. If I want 0.5 volts, then I want it less than 2 into 10 to the power 12. If I want 0.2, I want even less. So depending on the process, so let's say I'm choosing TSMC, they might have 3 flavors, or if XFAB might have just 2 flavors. And I just have to design within those 2 flavors, okay? And the last item is the, I just call it Q impure COX. And if you see in your book, I'll not go deep into that. It's basically the charges which are trapped inside the oxide. So far we are assuming that the oxides don't have any charge, but there are actually charges trapped in the oxide. And you have to, those charges also need to be overcome. When I mean by overcome, basically you have a negative charges, I need a field to end there. And that field has to come from the gate. So I have to put a positive charge to end it there to neutralize it. So if I have a charge, unwanted charge, I need to neutralize it. So in order to neutralize it, I need this amount of voltage. Whatever is the impurities trapped inside the oxide, plus there is an impurity which is called surface state trapped charges, that is between the interface. So it's right here at the oxide and this P substrate inference. So oxide and P-type interface. So these are called the interface trap charges. Okay, they're called surface state. So it's actually it's actually a quantum quantum mechanical phenomena which happens. Basically, your band bends so much that you create states which will attract electrons to get trapped there. And once they get trapped there, they're just trapped with the equivalent value of negative or positive depending on the trap states. And that's actually one of the major sources of noise in analog design. That's actually one of the major sources of noise as well. Okay. All right. So those are all the terms for VTN. So if I write it again, so let's see, maybe one by one, if you can direct me. Okay. What's the first term? Who can?
V flat band.
V flat band. Okay. And that's usually what? What is that quantity? It's the
One contact potential.
yeah, contact potential or the work function difference between the two end materials. So it'll be gate and the substrate here. Okay, what's the second one? Somebody else.
2
2
phi
2
phi f.
phi.
Okay, okay, 2 phi f. And this is what? This is
The work potential for the
conduction
surface.
for the channel to form.
Yeah, this is the
Voltage
surface
required for
potential for the
induction.
channel to form, basically.
Yes.
Yeah, and which is 2 times the Fermi potential of that substrate. And then, okay, what's the next one?
VOX.
What's that?
I by COX.
Uh, yeah, for VOX, correct. And what is that total term, which is Q, the bulk charge by the oxide, right?
VOX.
Depletion. And you remember this, we calculated from that depletion length, which was 2 times epsilon. That's the permittivity of silicon times the dopant concentration, which is Na here. And the potential difference between the depletion area, which is what? 2
Fierce.
2
Yes.
Vf, right? 2
Too
Vf.
fierce, sir.
So
You
that's
missed
that.
Q also.
So this is your depletion, right?
So you missed Q also.
Oh yes, sorry, thanks. So 2Q epsilon S Na by 2F. Okay, what's next?
Implanted
Implant,
Q.
right? So Q times whatever is the density of ions
The
per
V
unit square divided by, again, Cox, right? That's the voltage
COX.
I
COX.
need, right? And what's the last quantity?
Q
Impurity.
Q by
impure
COX.
by COX.
By
Yeah,
COX.
yeah. So all the impurities, the surface state and the impurities trapped inside the oxide. So that's Cox, right? So that's your total VT equation. Okay. Okay. Now tell me which is physics, which is what I mean by physics. I choose a material and it's fixed. I can't do anything. Which is controlled by the process guys. Which does the designer control? Like, for example, I choose a process. What can I control here? So flat band. So what can who is controlling this? Is it decided by physics or by the foundry, or the designer can control it? Can I control it? Like, can I take a transistor and change the flat band voltage?
No, sir.
Maybe foundry,
No,
sir.
sir.
No, sir. No,
Foundry.
sir.
So somebody said yes. Yes, what? Designer can control it? Is it Prachita?
I said no, sir.
Okay, so how does a designer control it?
Sir, we can only change the NA, that is the acceptance, and also the ND.
Right. So, okay, you're correct. So, if you remember, this was 2 kT over Q, ln Na nd ni square. So these are decided by the process, right? So these are decided by foundry. The designer can't do anything. Once I choose a process, I cannot do anything. The foundry chooses it, but the foundry is almost bound by other factors. So they actually cannot change it. So even the foundry will have a flat band voltage for a given type of polysilicon and substrate, which are decided for other reasons. Okay. So this is almost like material dependent. So I would say this is basically, they have chosen a material and you just live with it. Okay. What about this one here? What's phi naught? So that's also 2 kT, actually 2 times 2, which is 4 kT over Q. In case of this
ln
thing,
Na by Ni.
right? Same thing again. So this you don't have any control. This is physical. This is the only thing, but this is your p-type substrate. And in a p-type substrate, you actually don't have any control on it, because the p-type substrate is supposed to be highly resistive. Otherwise, they'll start shorting this thing. So this is foundry has control, but you can say this is pretty much whatever is the material, I'm just stuck with it, right? Okay, what about this? So you have Cox, you have epsilon S, you have Q, which you don't have control. That's physics. Epsilon S, that's physics. You can't control it.
Yes,
Again,
we can control TOX.
you can't control CO. How do you control COX?
Sir, TOX, oxide
Oh,
oil.
okay. You can, yes, I mean physically, but for a technology like, let's say you're designing in 28 nanometer CMOS, okay? CMOS. The core part of this technology is your TOX. So whatever it is, 10 angstrom or whatever it is, or 100 angstrom, that's the core part of your technology. That's what decides how fast a device is going to be. So you can't, so this is given for a technology. So if I'm choosing a 0.6 volt transistor, you know, NMOS, okay, this is given. I can't do anything about it. So this is also almost material dependent. And same thing, again, the Na is actually the dopant concentration for the P substrate, but the P substrate is decided for other reasons because of which Na is already decided, and COX is decided because of the type of device I want. Phi is decided because of the substrate I want. So this is also pretty much fixed. So when I say material, basically I'm saying this is fixed, this is fixed, this is fixed for a given device type. Okay, what about this?
This can be changed.
Yeah, this can be changed by the foundry without affecting any of the other stuff like the substrate, because that's the engineering part of it, right? So the foundry controls it, but that is pre-decided. So when I choose a technology, I might get a high VT, low VT, uh, and a medium VT device. These three flavors of, let's say, 1.8 volt technologies is it's a 0.18 micron technology I choose. They might give me these three. So it's decided by foundry, but it comes free-fixed. So I can choose either, let's say, 0.7 volt VT or 0.5 volt VT or 0.2 volt VT, depending on the type of circuit. If I want high performance, I choose low VT. If I want low power, I choose high VT, and so on. Okay, so that's also fixed by foundry. And this also, this is just what I call it is parasitic. Okay, the impurity is basically parasitic in nature. You don't have control on it. When they fabricate, this is what turns out to be. Again, you don't have any control on it. It is fixed and parasitic. Okay, so these are your quantities. So you can see the designer has no control on any of this. Okay, everyone
So,
follows this? Yep.
Biasing the substrate
so in the
with respect to source.
Okay, one by one.
sir,
So
yes, that's what I.
okay, what's the question?
Sir,
Sir,
if
biasing.
Go ahead, one like Prachita, go ahead. What's the question? Looks like same question.
yes, sir, yes, same question, sir. If we bias the substrate with respect to source, like if VSB is added to the depletion equation, like 5F plus VSB, sir, can we control
Yeah.
that VSB
So
per?
that's yeah, that's my next thing. So the only thing we can control, actually, before I do that, I'll give you a problem to work on, like VT. So let's take. So we did a calculation for VTN for NMOS, right? So take this, note it down, take this as a homework, and this will kind of give you an experience on how to become an engineer compared to what you have been doing so far. So for a PMOS, this will be N minus, and obviously your source will be P plus and P plus. You put an oxide here, you put a gate here, and this gate is going to be P plus poly. The reason is because this is getting ion bombarded by the same amount. So this dopant, let's say, is 10 to the power 15 dopants per centimeter cube. This is Na is 10 to the power 19 per centimeter cube. Okay. Uh, so what else do you need? Minus VP. Okay. So what I'm going to ask you is this. I want you to find out what kind of implant I should do and how much should I do. How much in the sense, you know, the term DI, which is basically ions per centimeter square or per unit area. How much do I need this to get a VTP of minus 0.6 volts? So that's your problem. Okay. And here again, so, you know, as a student or as a, you know, kind of a pedantic guy, you'll go and kind of look into all the equations for PMOS and all that and do it. But as an engineer, remember, you have all the ingredients you want. Like, let me see, where do you have it? So, for example, here. So, remember, okay, let me go back. Let's see which slide would be a better one. Okay, so let's just go here. So, for example, you already know what the work function difference between a N plus poly to a P minus substrate is. It's just reverse here, right? So what should this be? Same thing, QB over Cox. Now that's going to be just negative ion. This 2 phi S, what sign is it going to be? Because that was for Na. Now you have a N minus with Nd. What's it going to be? So forget this. Don't worry about the impure part of it. So basically calculate this and then figure out what this value comes out to be first. And then how much do you need to put it? That's it. Everything is there in this problem which you have solved. You can use this to solve this problem here. Okay. And that's how you should start looking at it, right? Every time I know people, get into the equations and so, which is fine. So the equations are good for you to, once you have understood it deeply and accurately, and you know the model, it kind of represents the model in very efficient way. Because if you start talking about, how the electrons are flowing and you start designing a processor, you can't be explaining it with electrons every time, right? So you have to take it to a point and say, okay, this is NMOS, this works like a switch. Then you go switch and you say, oh, this looks like an AND gate. Then now you know how an AND gate functions. Then you go to a LU. Then you say, oh, LU function. So you keep jumping from higher level. So during those jumps, it's okay to encapsulate them in equations or some sort of a heuristic. But you have to have an intuitive understanding of it. Otherwise, the equations are purely useless, right? If you're just taking every time trying to solve an equation, it's purely useless. Like, for example, right now when I'm giving you, if you are in that intuitive engineering mind, you'd say, oh, I know the phi ms, because the Fermi potentials are reverse in that case, it'll be negative. And since ND and A are same, opposite signs, but same value, the LNA over NI should be same, so on and so forth. I'm just kind of giving you some, vague guidelines, right? So that's how you should try solving problems, right? You already know some basics, use that and kind of intuitively use that. Then you'll get much deeper understanding of the functionality of other devices as well. Okay, so so take this, and so that make that as your homework problem. Like I said, I'm not grading for any grades here. This is for you to understand. Don't ask anyone. I mean, you can discuss for a healthy discussion, but taking in, just writing it down is of no use. Okay, so everyone's noted this down. Can I move on?
Yes, sir.
Okay.
Yes, sir.
All right. So, so what Prachita was talking about was you. So that's your P substrate, and so let's say this is your. So let's take NMOS. Keep it with NMOS for now. And this is your poly, right? So now let the example we have been taking as a capacitor, we do the same thing, but now we actually short this two ends too. Short in the sense same potential as the bulk. So all the bulk potential the same, and I still apply this gate voltage VG, right? So with respect to source here, which is, that's why it's called VGS, but essentially now all the potential are same. So this is ground, this is ground, this is ground, and your channel is formed right now, and it looks like a capacitor, right? So your channel is formed here, correct? And it's formed at the time when VGS is equal to VTN, right? And this is a reverse bias diode, so which means that there is a depletion. This is kind of a depletion area between. So this is all negative ions here, right? And this is that QB we calculated. QB we calculated. Now let's say and if you look at, so the PN junction is basically, this is the entire N part. Okay, let me choose another color here. So this is the entire N part now, right? And this is your P part. This part is your P part. So that's why you have this PN junction here, right? The giant diode. So that's your P part. Now let's say I take this voltage. So I apply, so I'm going to, just for argument's sake, I'm going to increase both sides by an amount, and we'll call that amount VSB. Okay, so we'll call this amount VSB. And we call it VSB because it with respect to bulk also. It's with respect to source, but in this case, because I'm changing the source voltage with the bulk, so that's why I call it VSB. Okay, because this is source, this is bulk. So VSB is a positive quantity. Otherwise, if I did VBS, it will be a negative quantity. So that's why we take VSB. So this is what I do. So if I do this, what happens? What happens to the depletion area? Who can say this? What happens to the depletion?
Depletion will increases.
The depletion area will increase, right?
Yes, sir.
I think somebody is unmuted. I mean, yeah, just make sure you're muted. Okay, so yeah, so what will happen is once I apply that voltage, so my depletion area, I'm just going to exaggerate it. My depletion voltage will increase. I mean, depletion width will increase with the depletion charge as well, right? Because I have increased the reverse bias voltage, because this is nothing but reverse biasing. So I had this diode, like this diode here. This is the diode I had. Previously it was 0. Now I have applied a reverse bias VR, right? You remember, once I do that, then this depletion area will increase. Okay. So previously I had this charge. Now the total charge is, let's say, some QB dash, right? Or in other words, I got some delta QB now when I applied that VSB voltage, right? So because of which my surface potential changed, and now my VT, my VG to invert that channel is a different value. And how do I find that value? The easiest way to find that value, or approximate way to find that value, is what is that gate voltage now I need? What is that delta VGS I need to move it back to QB, right? So if I put that delta VGS here, then I'll be back to QB, and then everything will be back to where they were. Everyone follows this? So basically I want to apply a gate voltage here such that this depletion is removed. Okay. Or in other words, because this is a negative charge, I have to add a delta V because I want positive charge to neutralize this basically. If I do that, then I'm back to that same surface potential because the surface potential hasn't changed. It's just that my VG needs to be more than what it was required before to get back to that. I'm sorry, the surface potential has changed, but if I can assure that all this differential charge, if I can provide it from my gate gate to source voltage, then I'll be back where I started from in this surface, and then it'll look like my original VT. Everyone follows this? This is actually a very approximate. In reality, it is a little bit more complicated because you can ask like, what happens to the surface potential? It looks like it's at 0. So one is, a vertical function, one is like a lateral function. But this is kind of a, it's what you find in textbook, and it's probably the easiest way to explain what is happening. But is it clear now to everyone? So basically what I did by applying a voltage across the source and drain, usually source, with respect to bulk, a higher voltage, is that I increase this depletion width, because of which the surface potential changed. And my job is to bring it back where it was before. And the way I can bring it back is if I can provide this charge through the gate potential here, then I'll be back where I wanted. Okay. So in other words, this delta QB is QB dash minus QB, because the QB dash, this is the total charge after I apply VSB, correct? And if you remember this QB dash, I can write it as 2Q epsilon S. If this was a p-type, it is Na. And this quantity now will be 2 phi F plus VSB, because that's the positive forward bias voltage. That's the charge, total bulk depletion charge after I apply the source to bulk voltage, correct? And then the previous charge was, before I applied it, was 2Q epsilon S Na times 2 times phi F. And if I kind of take some common factors, this is going to be 2Q epsilon S Na times root of 2 phi F plus V plus VSB minus, sorry, minus 2 phi F. Okay. And if I divide this whole thing by Cox, then that's that extra delta VGS I need for it to go back to that VTN. So in other words, if I write the expression for VT now, so I'll call this VTN as a function of VSB, then it is what it was at VSB equals to 0, which I'll call it VTN 0, for example. And then in most text, you'll see this gamma quantity, which is this here. So if I, this quantity here times this quantity here. So when VSB is equal to 0, then it goes back to VTN. Otherwise, it's this quantity. Okay. So, and you see this any textbook, you'll see that quantity. So that's, so you, what is the effect of this? If you increase this source voltage with respect to bulk, then your VT goes up, right? So for example, I'll give you an example in your thing. All of you are familiar with, a little bit familiar with gates now. So in your NAND gate, you have two NMOSes, right? This is connected to some A input, this is connected to some B input. So this bulk is usually connected to ground. So is this bulk, right? So typically this has to be, let's say this is conducting some current, discharging this gap. So this voltage is at a higher voltage than this voltage, than the ground. So which means that this is ground, 0 volt, but this source is not. So that's your VSB, which means that the VT for this device is greater than VT for this device. Okay. So VT, let's say this is VTA, let's say VTB. So typically in a CMOS, your NMOS, your VSB is always higher unless you deliberately make it lower somehow. VSB is always a positive quantity, or your source is higher, which means your VT increases. In a PMOS, it's the other way around, the VT decreases. So your source voltage is always lower, so your VT decreases because it's a negative quantity. So it increases in the negative quantity, but the mod of that increases, but if you take the negative value of it, it decreases. Okay, so that is the designer control, because now this the designer can control it, but most of the time actually it's the other way around. The designer doesn't want to change it. It's because the way the configuration of your transistors are, you just end up with a different VT. Just like, for example, here in this thing, most of the time the designer doesn't want this, but it's just because you have it connected this way, you just end up with this. Does this make sense?
Sir, yes, sir.
Yeah,
Yes, sir.
it's clear, right?
Sir, we are in.
Yeah, yeah. Go ahead.
So
Go ahead,
yes, sir,
Rich.
that VSB we are yes, sir, that VSB part we are increasing the source voltage with respect to the substrate. So our depletion rate is increasing. So sir, you said VGS. We need to adjust the VGS in order to get back our original QB. So
Yes. No,
we
no,
have
no.
to
Sorry,
adjust
sorry.
the
Not,
value of
not.
VG there, no?
No, no, no. Not original QB. Maybe I misspoke it. Original phi s, the surface potential here. This one. Original phi s equals to 2 phi f. That's what I want. Okay.
Yes, ma'am. So we have to adjust the value of VG there
Yeah, yeah.
in
So
the
it's
VGS
just a way
to
of
make it
explaining.
to the original.
Right. It's just a way of explaining why the VT is increasing. It's just a way of explaining, saying that in order to get that same channel, now I need a higher voltage, because I have to, just like we have been doing so far, right? I have a charge here, I have to apply a voltage to neutralize this. I have some charge stored here, I have to neutralize this. Similarly, now if you increase this charge, if I want to neutralize it, I apply a gate voltage as well, right? So it's kind of the similar line of thought. Does that make sense?
Yes,
Yeah.
sir, but in that way, we have to decrease the value of VG, like whatever we are providing, so that the depletion layer will decrease.
No, no, no. You're trying to neutralize it. You're trying to account for it.
Okay.
So, guys, just please mute whoever is. Okay. Yeah, you need to account for it. You're not trying to decrease it. So the line of thought is, if I applied this surface potential, this much charge will form in the channel area. Sorry, this much charge will form in the channel area. Okay, but once that forms, it will actually change this surface potential, because now your depletion looks like this with the same gate voltage, which means that this PS probably increased or decreased or whatever happened, right? But that's because of this source to bulb voltage, not because of the gate. So what we are trying to do is, we're going to say, oh, what can I do from the gate side so that it looks like as if I got this from the gate, because then that will bring this surface potential back to 2 phi f. You got it? So it's kind of a circular argument, but I don't know if there is a better way to explain. Maybe just read some couple of more texts, but I'll think if there's a better way I can explain it. So essentially what you're doing is you're changing this in a very simple manner. When you're changing the source voltage, you're basically modifying the surface potential. Your key is surface potential, right? So this potential with respect to bulk is what you want 2 phi f, greater than 2 phi f. That's your key, right? So if you're doing anything to change that, the question is, what do I have to do on the gate side to bring it to back to that 2 phi f? That will tell you what your VT is. Okay, so it's a way of explaining the VT increase. That's not what you do in the circuit. It's just a way of explaining how your VT is increasing.
Yes, sir.
Hello, sir.
Yeah. Puneet, go ahead. You have
So
a
I
better
think
explain. Go ahead.
no. So I don't want to explain. Even I have a question.
Right, right.
So I think what she was asking, and I also have the similar question.
Yeah,
So what we are doing, we are increasing the voltage of source right now.
right,
So like source and the drain, you just increase the voltage of that. That
right,
means the source is now on a higher potential with respect to the bulk.
right,
When we are talking about VT, then we are talking about the gate to source voltage. We are
right.
talking
Which is
about VGS, and we are
right,
saying that at what particular VGS the channel will form, and that is with respect to the source.
right,
Now, so that means what she is asking is even have the same doubt, like how we are going to explain this, because the potential difference between the source and the gate, if I will talk about the source and the gate, that is like in initially whatever the VG voltage, now you have just let us suppose the VG was initially is a 1 volt,
uh-huh,
and at the source you applied 0.5 volt.
right.
The potential difference between gate and the source, now it become zero point 0.5 volt.
Exactly. So
Now
your question is like, why not just apply 0.5, right?
yeah, means even if I will apply the zero point 0.5, so if
Right,
even if I'm saying even if I will apply the zero point 0.5, it will compensate whatever I'm doing.
right,
In that particular case, whatever the VT remains, now VT come back to the 1 volt.
right,
So, but if we will explain the way you explain, like and the way it looks to me also. So the VT voltage which we are talking right now, it is with respect to the bulk.
Oh, yeah. So I probably should make that correction. So when I meant bulk, I'm still referring to source because the source is not changing, because we're talking about change in voltage, right? So yes, we should always talk about source because everything is reference to source. So your question is, I guess maybe I didn't follow the. So is your question? So let me just draw it again. So let's say I just I had this, right? So I had VGS equal to VT and a channel formed. And so previously I had this to ground. So let's say we have some other voltage. So forget about that, some slower voltage here. So what I'm doing is I'm saying now I'm applying a voltage like this, right? Some VSB, because this is ground. So I'm applying that, right? So that's what I did. So your question now is VGS is, so let's say for example, the example you gave, we started with 1 volt. We started with 1 volt, and let's say VT was 0.9 volts, VTN. So a channel was formed. Now let's say I put 0.5 volts. So your question is your question like, why is it not 1 minus 0.5, 0.75? So I just compensated by doing 1.5 and then minus 0.5. It's still VGS is 1 volt, and then we are back into the same deal. Is that what you're asking, or?
Yeah. So
Okay,
my question is like, if because this when it comes to the VT, the
right,
reference one is a source,
right,
and if the reference one is a source, and now when you are increasing the reference voltage itself,
right.
then so uh,
Yeah. So I think maybe I got the question. So when I increase this by 0.5, right? So VGS is now what? 0.75,
no,
right?
point 0.5, 1 minus 0.5.
Sorry, 0.5, right? 0.5.
Yes.
Now let's say VTN was 0.5 volts, right?
Uh,
Without, when VSB equals to 0.
yes.
Now
Okay.
the question is the channel formed? The answer is no. Because
Because
now the VTN is probably 0.7, I mean 0.512 or something like that, depending on gamma. So which means that if this is 0.5, I need to be 1.12 volts for the channel to switch on. But what I'm saying is that that's why I said you have to be careful, because this explanation is a very simplified one, because the channel is actually having the same surface potential. So you might ask like, oh, the channel is sitting at 0. It's not even 2 phi f. So that's why I said it's a very simplified one. But if
Like,
you look at,
so
yeah,
still I have confusion. So just
right.
take the VT voltage itself. So like here VGS,
Okay, so let's start with VSB is 0, right?
yes,
So let's
VSB
say
0,
VSB 0 and VTN is 0.5 volt,
and
right?
you have applied at a gate 0.5 volt itself.
Okay. So let's say the gate voltage is 0.5 volt. So now
That
the
means
channel is formed, right?
yes, channel is formed.
Channel is formed. Now what I'm going to do is I'm going to apply a small voltage. Let's say a 0.1 volt here. This is VSB, right?
Yes,
Now VGS is
0.4.
equal to 0.4. So you might say, okay, I'll just increase this to 0.6, right?
Yes.
And it'll turn on, but it won't. You have to increase this to whatever is the new VTN now is. So let's say the new VTN is, let's say 0.55. I can't do 0.6 anymore. I have to do 0.65 to turn this voltage on. Because of this, the source to bulk difference, now my VTN is a new VTN.
Yeah. So I got that point, but again,
I guess your question was something else,
no,
or
no. Question was this only. I got this point also. Now, when it if we will map it with the explanation, so in the explanation,
so in the explanation, what I'm saying now is you, I did 0.1, right? And you said, oh, just increase this to 0.6, right? 0.6, and your VGS is 0.5 volt and VT. But what I'm saying is that because you created that depletion, which still exists, that depletion hasn't changed from this diode, which is this one here. You have to compensate that on the channel side before you can come and invert this channel here.
okay.
This part here. Because what will happen is this depletion will affect your phi s. And I have to change this gate to source voltage to come back to that original phi s of 2 phi f. And now that's 0.55 or whatever that value is. I just gave a number.
So how will we change? Like, how will we come back and be specific, like
No, it's not how you
to
come
that value?
back. So just like the way we explained, so if you give 0.1 volts here, so for example, I write the ID equation. I think I haven't come to that, but I think I've already talked about the ID equation. So ID is mu n Cox W over L VGS minus VT. Let's say this was in saturation, right? VT square. So what we are saying is that I give 0.1 volts. So let's say this was 0.7. Then my ID would be whatever this beta term is. Then VGS is 0.7 minus 0.1, that is 0.6. VTN is 0.5, 0.1 square. But what I'm saying is that no, VTN is not 0.5 anymore, it's 0.55. So your current is actually lower now. So this new ID for a given VSB is lower now.
Yes.
So Puneet, looks like you're still not convinced.
No, sir. I'm convinced. I'm just trying. Like, okay, how should uh, how should we can easily explain this thing?
Yeah, no, I know.
So,
It's a
but I think because the explanation which you gave, that is
it's
the
actually a standard
easier.
textbook
I-
explanation,
No, so
but I
that is easier than what I usually give. So that's the reason I'm just thinking like what
how do you
modification.
what's your explanation? Actually, might be easier actually. Well,
So
what's your explanation?
what I usually do, I just keep source at a ground only
Yeah.
and just lower down the bulk voltage.
Yeah. Absolutely. Actually,
So
that's even I
just to
actually like.
give whatever we were doing, just to give them the same understanding. Like, okay, if we will lower down the bulk voltage, it's the same thing. Like we are talking about the body biasing basically.
Right.
So
So this is what you do, right?
yeah. So I
Got it.
just do in that particular way. Like reference, I'm not touching. Now I just change the bulk voltage, and then I just explain them like, okay, if
No,
bulk is going to be the lower side, then what is going to happen within that
right. Actually, this is, I think, now that I think about it, it's probably, I mean, in circuit, we never do this, but for
Yeah.
explaining, I think this is better.
Yes, actually, that's even that's a thing. Like every time, I also like in a circuit we never do in this particular way, but I never find out any other way to explain in a better way.
Yeah, no, that's actually better way. So I can, hold on a second, maybe I'll do a few.
Sir, in this way, sir, hello.
Yeah, go ahead.
In this way, you can means actually suppose VS, suppose VS we are increasing positive voltage, source voltage we are going to positive voltage. So XD, the depletion region, though source and bulk, there is a means opposite, means it's a reverse bias. So XD increases the depletion width.
Depletion width?
Suppose initially source and bulk in the same potential, means 0, 0.
Right.
Yeah. Now source voltage increases.
But yeah,
we are increasing. Deliberately increasing. Hello.
Yeah, go ahead.
We are increasing source voltage.
Yeah.
And then the depletion would increase.
Yep.
Then that depletion charge also increase. Though,
right.
Yes, once depletion charge will increase, then surface potential that will increase.
No, see, that's where the confusion comes. So when the depletion, because of the diode increases, the surface potential actually drops. It doesn't increase. It might increase because of, and that's why you have to increase the surface potential to come back to that point. And that's why I said it's very confusing. But so that's what you are trying to get back to. So for example, this was your original depletion. But yeah, I like what I think Puneet is saying.
No, what I understood, though VG is constant, okay.
Yeah.
So once the charge of depletion will increase, phi s
Right.
increase, then phi ox will decrease. Oxide voltage.
Phi ox will, yes, exactly.
Yeah.
Not phi ox. There's no phi ox, but the V ox will remain the same, but phi s will decrease. So that's why you need to increase the gate voltage to get it back to wherever you want. So basically,
Yes.
what you're saying is that you originally had this, right?
Yes.
You originally had this. Now I added this substrate bias, which I think Puneet is right. It's better to explain this, although we don't do this in the circuit. So I apply a negative substrate bias. Because of that, now my new charge is this, right? My new charge is
Yes.
this. So you're saying, I think I know where you're coming from. You're saying, oh, if my depletion is looking like this, then this phi must be at a higher voltage, not at a lower voltage, right? That's what you're saying.
Yes, yes.
But this charge has come not because of your gate. This charge has come from this. And that's what I'm saying is that in order to get this phi s such that this depletion looks from VG, you have to increase it by that amount.
Yes.
Right? And that's your potential you require on the gate side. So yeah, so going back to that same explanation we are doing, just so that students are clear. So if I apply a VG, what did we say? 0.5 volts. 0.5 volts with respect to source, and there's some VD volt here, let's say lower value. And so obviously the substrate is grounded in this case. So VTN is equal to, let's say 0.5 volts. So the channel is just formed, right? So instead of changing the source voltage, we change the bulb voltage, but we do a negative. So you do VSB here with this battery. And let's say the VSB was equal to 0.1 volt or something like that. Now the channel will turn off. So you have to apply now the new VTN is equal to, let's say 0.55 volt. So I need to increase this gate by 0.55 volt to bring that channel back up again. So this is what you're saying, Puneet, so that you're not changing the source voltage at all.
Yeah, I mean,
Yeah.
this is something uh, helpful.
I think I
Yeah,
agree that you don't want to confuse with two things, like the
but
source is changing, the bulk is changing, but yeah.
yes. So here, students have another question which they can confuse. So I'm just doing that particular part. So like here we are just explaining like there is a predefined depletion width.
Hmm.
So we are talking about like, okay, the source voltage is there and the gate voltage is already there. The channel was there. The depletion width was there. What
Right.
if the depletion width itself is not there? So that means the bulk is on a negative the very first day, and the gate there is no voltage. Then what is going to happen? So like source, gate, and the drain, they are at a zero potential. And if
Okay, let
you
me
are going,
draw. So, so basically you're saying, yeah, I think I get the picture. So basically this is just floating, you're saying.
so I'm just saying this, the way we usually start like, okay, source and the drain both are at a zero potential, and the
Okay, so this is,
gate also at a zero potential, and the bulk also has zero potential. So usually we
okay,
start at this particular place. Like now, if we will increase the gate, then gate potential, then what is going to happen?
right. The
The
normal
same,
VT.
yes,
Yeah,
normal operation. Now in
right.
the normal operation itself, now what I am doing, if I am going to decrease the bulk potential.
Okay, so now you apply a negative potential here and start
Yeah,
basically
just to
increasing.
explain everyone, like maybe tomorrow some of you will come and you will say like, okay, what is going to happen here? So now from here itself they can also analyze like, okay, in place now we are not touching anything on a gate side. Now
Right,
first think what is going to be the condition at the different junctions.
right,
So like all the PN junctions, that's the depletion rate at the PN junction, that's going to be more compared to the previous one, because previously it was 0 0,
right.
0 at N, 0 at P. Now it's going to be reverse bias. Plus, because it is a negative potential, then we have to understand like, so the confusion come from here. Negative potential, then at this particular position, what is going to happen? The electrons are already pushed in upward direction.
Yeah, so you're saying this is already formed. These
This,
depletions are already formed,
yeah, this depletion is already formed.
right?
So now I'm just discussing, like, sir, what
Yeah,
the
and I
question
think that,
come.
right, I think this is where the Santanu's question was too, and that's where I think it's a little bit tricky explaining this, because what
Yeah,
Santanu is saying that, okay, this is the same condition as when I had a positive
gate
VG,
voltage. Yes.
positive voltage. So why is it taking more? Why is it not less?
Yeah.
And the thing is that because this surface potential now is because of the band bending of the PN junction, not because of this. And the surface potential which has come here is actually lower, not higher now. And how? Uh, yeah, you have to draw the band diagram, but I don't know if I can draw that right now. But it is actually lower. It is not higher. So basically the argument is that I want the VG to be such that this comes from this potential, and that will tell me how much extra voltage I need for the surface potential because of the depletion from the gate voltage, not from the diode. I think that's the argument. But yeah, if you look at it from, but the band diagram is a little bit complicated because now you have a lateral and a vertical structure, right? So it's I don't know if they actually do this with the band diagram. It becomes a little bit tricky.
Yeah. So that's another question. Like they usually ask. And now, if
Right.
in this particular situation, if we try to explain them, like in a books, nowhere it is written. No, nowhere it is written. Like, okay, what is going to happen? So
Right.
like,
Actually, nobody even talks about the surface potential. I'll see. Maybe Civitas has this when it talks about the VSBL. Civitas usually has a very deep. But yeah, usually all the the circuit books, they'll just say QB displaced, QB displaced, and obviously it's kind of a very half-fast, but usually that's enough to like
yeah.
just
Then
like
most of the
have
book,
faith
what
on
happened?
people and keep going.
So most of the book, what happened, like they the very initial condition, like the default one, they they come up with the equation, and this particular concept, they never talk about the formation of a channel and all these things. They always talk about in terms of the equations. They
Yeah.
always mention like, okay, in this particular equation, if we will increase the VSB, then you can see,
Right.
okay, VSB square is there, and that's
Right.
the reason it
Yeah.
will
Yeah.
always increase the
And
potential.
that's the problem because students also they just do that. It's like just tell me where should I plug it.
Yeah, so my that's the reason I was just saying, like, okay, that explanation, the way you explained, that looks to me like this type of confusion will not come. In my explanation, this is the confusion, because the student, they usually come and they say like, okay, like how to overcome this particular part, because already depletion width is there. Now
Right.
we have to apply a potential which can just attract more electrons and the channel will form.
Right. And yeah, the explanation is actually you want to neutralize that charge to bring back the phi s. But yeah, you have to draw the band diagram to show that. And if I draw the band diagram right now, I think I'll confuse everyone. I have to also look at it. When you have a depletion, I think what happens with the if you just take like if you just take this portion and do a band diagram. So like for example, this is your oxide. So normally you have that, and you want to apply a more potential so that it bends. But in this case, because the depletion is coming from a side, it actually goes up. But I think most people will ask, well, why is it going up if you already have a depletion here?
Yes, yes, yes. That's the
because
problem.
because this potential difference should give you this depletion width, but that's because of this PN junction here. So if I take this PN junction and draw the band diagram, like do this, then yes, this band is like completely bent like this, but that's different from this one. And I don't know what's like a more intuitive way to explain it. I'll see if I can find a better explanation maybe in CVDs.
Yes,
It should be
CBD
should be a
may
better
have.
one.
Yes.
Sure.
Okay. I think students are all like, we need chai now. Let's go home. Okay. So I think maybe because I wanted to do the current equation, but maybe it's like maybe overload now. And unfortunately, I think accidentally I deleted all my, no, it looks like I do have my annotations. Okay. Okay. So maybe I'll just stop here and, okay. Actually the capacitor one is very important. So yeah, the voltage dependent on the capacitor. Let's do it next time. So we'll start with the voltage dependence of the capacitance one. And that's a very critical one for IC design. I think you should have a really good understanding of it, and then we can explain the ID equations. ID equations actually will be very fast because we already have done the resistor formula and all that, so that should be very quick. So I think the capacitor is the one where I'll probably spend a little bit more time. The voltage dependence, and just mention a little bit about the frequency dependence as well. Okay. So I think we'll just stop here, and actually the next class Puneet, it's okay, right? Santanu taking the standard cell. I think he did one good presentation on standard cell for Xavier last year. So I was thinking, because you're kind
Yes,
of
sir.
referring to standard cells.
Yes, yes,
So
sir.
Yes.
No doubt. So he should take it.
yeah.
Okay, sir.
So so Santanu, that's okay, right? So next Monday, I
Yes, yes,
think we'll do that.
yes,
So Santanu has a really nice presentation on standard cells, talking about what is standard and how are the different standard for routing this and that, and just basic format of the lib format, which Puneet had been going into in detail with the STA1. So I think next Monday we'll do that, and then again we'll continue with the MOS one after that. So that way, I think Puneet, when you're covering some of the lib format and standard cell part, maybe it'll be a little bit more, because these people, they haven't done any design or any standard cell work yet. So it's a little bit abstract for them, I think.
Yeah, yeah, sure. So I think we already discussed, like that should be good for a student anyways.
Okay. Okay. All right. So any other questions?